All right, so if we're going to factor the difference of perfect squares, picking up from where we left off yesterday, then we're looking for two terms. They're both squared and joined by a minus sign. Now, if it's the sum of perfect squares, can't do anything with it. It's got to be the difference of two perfect squares. If that's the case, then we're going to factor it into conjugates. And we've done this in reverse. We saw yesterday on the class starter and today on the class starter that if we recognize two sets of parentheses as being conjugates of each other, then they're going to become the difference of two perfect squares, so that works in reverse. If we recognize the difference of two perfect squares, then we factor it into conjugates. So looking at some examples, let's see. So first thing, no matter what technique that we intend to use, what's the first thing that we look for? A GCF. So we're looking for anything that's separated by an addition or subtraction sign outside of parentheses. So here's a subtraction sign, and that's what separates those two terms. Is there a GCF among those two terms? Yep, what is it? 4x squared minus 9. They both have a 4x squared minus 9. In fact, they both have 4x squared minus 9 raised to the first power. So we'll take out the 4x squared minus 9, and we're left with x squared minus 16. Because once we take that 4x squared minus 9 out of each of those terms, and all that's left is the x squared minus 16. And now we recognize difference of perfect squares. 4 is a perfect square, 9 is a perfect square, and then 16 is a perfect square. So we're going to be able to factor each of these into their corresponding conjugates. So what would be the conjugates that correspond to 4x squared minus 9? And then the conjugates that correspond to x squared minus 16? There you go. All right. There's difference of squares. Can't do a whole lot with that in terms of making it more challenging. All right, same thing with this. We can start by looking for a GCF. And here's the minus sign. That's outside parentheses. So what is our GCF? X squared plus 9. Once we remove that x squared plus 9, what's left over from this first term? And what's left over from the second term? 1, right? Once we take that x squared minus or x squared plus 9 out, we have to have a placeholder there, and so we put a 1 in place of that that term here. Since everything's been removed, the x squared plus 9 has been removed. Do we have any difference in perfect squares? Yes. Yeah. Not the x squared plus 9. We have to leave that alone. That's the sum of perfect squares. But the 4x squared minus 1 would be 2x minus 1 and 2x plus 1. I good on 2? Moving right along here. Let's do this one. X plus 1 to the non-halves minus x plus 1 to the 5/2. There's the subtraction sign that's outside of parentheses. It's going to separate our terms. Is there a GCF? There is. We know that both of those terms have an x plus 1. Then we just have to decide the exponent, but we always take out the smallest one, which in this case would be 5/2. And then we're going to see what's left over. Originally, in this first term, I had x plus 1 to the 9/2 power. I took out 5/2. So what's 9/2 minus 5/2? 2. So x plus 1 squared. And then we took this entire term out. So what's left over? 1. What's left over inside this parentheses? Is that the difference of perfect squares? Yeah, because x plus 1, even though it's a binomial, it's squared, and 1 is a perfect square. So what we have here is the difference of two perfect squares. And if you didn't recognize that and you FOILed this out and then eventually factored, it would work out still. But it's nice if I can recognize that as the difference of perfect squares. And so I'm going to have x plus 1 and x plus 1 minus 1. And so finally, we have x plus 1 to the 5 halves times x plus 2 times x. And there would be our completely factored form. Everybody good on difference of perfect squares? Moving right along to our next form. We've seen how to factor when it's a trinomial, when there's 3 terms. We've seen how to factor when it's the difference of perfect squares, which would be 2 terms. We have a method of factoring that we can use when we have 4 terms. And you've learned that before, and that's called grouping. Not a real fancy name. Grouping simply means that I have 4 terms, and really I can use it if I even have more than 4 terms. If I were to have like 6 terms or 8 terms or some even number of terms, I could try grouping. But what we're going to do is we're going to break this expression up into smaller groups. So if we have 4 terms, then we might group the first 2 together and the last 2 together. And see, in doing that, if we can do some GCF work that's going to allow us to factor. If we had 6 terms, we might group the first 2, the middle 2, and the last 2, or the first 3 and the last 3. If we had 8, same thing. We might group the first 4 and the last 4, or do groups of 2, or whatever we think might be helpful for us in terms of factoring. But we're going to group different pieces together and then look for a GCF along the way. So, if I have any examples of this, let's see. I just have to make some up. Yeah, good. All right, so we see this example here. You have 18x cubed minus 15x squared minus 30x plus 25. And we notice that, first thing we always look for is a GCF. Would there be a GCF for all 4 terms? They don't all have an x attached to them. They don't have a number that goes into all 4 of those numbers evenly. So we can't use a GCF to start with all 4. But we notice that there are 4 terms. And 4 terms is an indication that we can use grouping. And just as the name implies, we're going to group the first 2, and we're going to group the second 2. But there's a problem by grouping it like this. What have I just done? I did make it a binomial, and how does that affect this subtraction sign? Yeah, grouping it like this would now cause a 25 to be negative. But is the 25 negative originally? No. So I got to be real careful with my grouping. I got to make sure that I handle addition and subtraction signs appropriately. So what I'm going to do before I group is I'm going to make just the 30 negative and then group. Okay. So now that's a negative 30x plus 25, which is what it was originally with the subtraction sign. So we've grouped the first 2, we've grouped the second 2, and now we're going to take out a GCF. So what would be a common factor to the first 2 terms? 3x squared. And then after I take that 3x squared out, what's left? 6x minus 5. What would be a GCF for the second 2 terms? 5, and we're actually going to take out the negative because what we want is what's left over to match what we have here. So once we've taken out a negative 5, what's going to be left over? 6x minus 5. All right, now this just becomes another GCF problem. Now I have a plus sign that's not in parentheses. And what do those two terms have in common? 6x minus 5. And what would be left? 3x squared minus 5. And we're done, right? Because we can check to see there's 3x squared minus 5 factor any further, but it's not the difference of perfect squares, so nothing we can do with that. That's grouping. They have group the first two, group the second two, be careful about any subtraction signs, and then look for GCFs within the groupings and then overall. Okay? So try that one. You don't feel well. Okay, so we'll group the first two together. We'll group the second two together, but we got a minus sign, so we got to be mindful of that. So we're going to make the 5 negative. So now, what is the GCF in the first grouping? And that would leave me with, and what's the GCF in the second grouping? Negative 5, and that would leave me with, and then I'll notice that both of these have an n plus 2, so I'll take that out, and I'm left with 4n squared minus 5. And you can see how it might easily turn out that what's left over here could be the difference of perfect squares. This one isn't, but could very easily happen, and we would have to continue to factor. You know, it could be that if we were going to factor, if we had like 6 terms and we grouped the first 3 together and the second 3 together, then it might turn out that something that we factor out could be a trinomial that would be factorable. So there's a lot of different options of what could happen in carrying further with grouping. So when we say, when the instructions are to factor completely, you got to check for every different level of factoring, every different method of factoring along the way. So I think grouping is something we feel pretty confident with. So our last method of factoring, and you learned this one in Algebra 2 with trig, is working with a sum and difference of perfect cubes. For perfect squares, it's got to be a difference. You can only factor the difference of perfect squares. But if we're dealing with perfect cubes, we can factor 2 terms that are both perfect cubes, whether it be a sum or a difference. Okay, that's one distinguishing mark here, is sum or difference. And I've given you the format for how we're going to factor the sum or difference of perfect cubes. Now looking at that, I mean, that would be hard to memorize that format, that if you have a cubed plus b cubed, it's going to factor into a binomial, a plus b, and then a trinomial, a squared minus ab plus b squared. And so what we've done, or what I did, is I came up with a little mnemonic device that's easy for us to remember in terms of determining that trinomial at the end. And so you're going to start off with just determining the binomial. And the binomial is the cubic root of each term. Okay, so the cubic root of a cubed is a, the cubic root of b cubed is b. If it's a sum, then the binomial is a sum. If it's a difference, then the binomial is a difference. Okay, that's the easy part. Then, to determine the rest, this mnemonic device is SOPs, and your altitude trait teacher may have taught you that. Okay? Once you have the binomial, then the S stands for square. Okay? This is new to you, and you don't remember that. You might want to write that out. The S stands for square. So we're going to square that first term. Whatever A is, we square it. And the O stands for opposite. So if this was A plus B in the binomial, then now this sign is going to become subtraction. If it was subtraction, A minus B, then it's going to become a sum. Then we do the product. So we're going to multiply the two terms A and B. Then a plus sign, regardless of whether it was a sum or difference. That second P stands for a plus sign. And then we square the last term. So square, opposite, product, plus square. And that helps us in determining the trinomial that's left over after we've calculated that binomial. Okay? It's important for you as you're factoring these to recognize perfect cubes. You're familiar with perfect squares. You recognize quickly that 1, 4, 9, 16, 25, 36, 49, all those are perfect squares. You may not recognize the perfect cubes as easily. We know 1 is a perfect cube. 8, that's 2 cubed. 3 cubed is 27. 4 cubed is 64. 5 cubed is 125. 6 cubed is 216. 7 cubed is 343. Okay, so if you see those kinds of numbers, then you'll recognize that. If you're not sure, then just do a little trial and error. If you got 729 and you're not sure if that's a perfect cube or not, then try 8 cube, try 9 cube, and if any of those come out to be 729, then you'll know that 729 is a perfect cube. Okay? So looking at some examples of that. We have 128x to the 4th minus 250x. Of course, we always start by looking for a GCF. That's always the first step. And is there a GCF here? Yeah, 2x, which is going to leave me with 64x cubed minus 125. It's two terms again. So 2 terms, if we're going to factor that, it might be the difference of perfect squares, or it might be the sum or difference of perfect cubes. In this case, because it's an x cubed, then that's kind of leading me to think that it's probably going to be the difference of perfect cubes, but let's make sure of that. Is 64 a perfect cube? Yep. Is 125? Yep. So this would factor as difference of perfect cubes. So we're going to write a binomial and then a trinomial. And the binomial is going to be the cubic root of each term. So what's the cubic root of 64x cubed? And the cubic root of 125? All right, and we keep that subtraction sign. So there's our binomial, and then we do SOPs. So 16x squared plus okay, so square the first term, so 4x squared is 16x squared. Then the opposite sign, so it's plus in this case. Then the product, 4x times 5 is 20x. Then plus, and then square the last term, and so that would just be 25. Now, one thing to keep in mind when you use SOPs is that trinomial that results is never factorable. Okay? The trinomial that results is never factorable. So you don't have to go any further. That's good news. Okay? That's 16x squared plus 20x plus 25. If you tried, you won't get anywhere with it. Okay? Now let's try another one. We have x to the 6th minus 64. Now, we actually have some options here. 64, is that a perfect cube? But it's also a perfect square. X to the 6th, is it a perfect square or a perfect cube? It's both, right? Because 3 goes into it evenly and 2 goes into it evenly. So if I were to treat this as the difference of perfect squares, what would the conjugates be?
x cubed minus 8 x cubed plus 8. And you would just do.
Yeah, and then those are both cubes, right? So we're going to have a binomial and a trinomial. And then for the x cubed plus 8, we're going to have a binomial and a trinomial. So what will be the cubic root of x cubed and 8?
X minus 2.
And this one will be x plus 2. And then we'll use SOPs with each of those to get the trinomials. Squared, opposite, product, plus squared. And then over here, the trinomial would be easy, easy, huh? All right, give that one a go. What's the GCF here?
3xy.
3xy. And what's left over? All right. 27 and 8 are both perfect cubes. We can factor the sum of perfect cubes, so we're still good with the plus sign there. X cubed is obviously a perfect cube, so is y to the 6, and 6 is different. I mean, it's divisible by 3. So we actually have the difference of perfect cubes, or excuse me, the sum of perfect cubes there. So we'll have the binomial and then the trinomial. What will be the cubic root of 27x cubed? And the cubic root of 8y to the 6? And then we follow with SOPs. So we square the first term, opposite signs, product. And again, the good news is that trinomial is never factorable. So we don't have to bother with trying to factor it any further. Everybody remember sum and difference of cubes? If you remember that little SOPs mnemonic device, then that kind of takes care of everything for you. I don't think we need to bother with that. This one we can do pretty quickly. You may not even need to write this one down. Again, we look for a GCF first. The plus sign separates our terms. And what do those terms have in common? 4x squared minus 1, which we know is going to be the difference of perfect squares. We're going to be left with 8x cubed plus 27, which is the sum of perfect cubes. So the 4x squared minus 1 will factor into conjugates. 2x plus 3, and SOPs would give us 4x squared. Everybody feel good with all that? think of factoring as not one that's new. So I really just kind of call this special forms of factoring. And that would be that, in cases where it looks like a trinomial, but it's not a quadratic trinomial. It's not, x squared in the first term, x in the middle term, and a constant at the end. And we've done some that are a little bit special, like if we had two variables where we had to ignore one factor, or if we had to make a substitution, we could do that. But there's also cases where you have a trinomial, it's not quadratic. It might be quartic, where the biggest exponent's 4, or biggest exponent might be 6, or something like that. But what you're looking for in cases like that is, if it's a trinomial, if the middle term's exponent is half the first, then in those cases we can make an attempt to factor. And because with quadratic trinomials, it fits that bill as well. In a quadratic trinomial, the first term has an x squared, the middle term has an x for the first power. That exponent is half the first. So if we have a polynomial or a trinomial that has an x to the fourth in the first term, if the middle term is x squared, and we might be able to factor that, or we can at least attempt to make a factor there. If the first one's x to the sixth, middle one's x cubed. The first term has an x, the middle term has an x to the 1/2 power. Okay, all those, we can attempt to factor them as trinomials because the middle term's exponent is half the first. And we're going to look at a few examples of that. But then here, I just gave you some hints for factoring, which are nothing earth-shattering. We always look for the GCF first. If there's two terms, then it might be the difference of perfect squares or the sum or difference of perfect cubes. If there's three terms, we'll factor it as a trinomial, particularly if the middle term's exponent is half the first term's exponent. And if there's four terms or more, really, we'll use grouping. So, going back to this special case, I was mentioning, here we have x to the fourth minus 5x squared minus 36. And you probably did some examples like this back in algebra trig, where the middle term's exponent was half the first. We're going to treat it like any other trinomial. Okay? So we're going to follow the same procedure of needing two numbers that multiply to negative 36 and add to negative 5, which would be what? Negative 9 and 4. Good. So our coefficient of the first term is 1, so I'll do 1 over negative 9 and 1 over 4, which neither of those reduce. But instead of using an x here, it's going to be an x squared minus 9, and then an x squared plus 4. Because when we FOIL out, we want to make sure we get an x to the fourth in that first term. So x squared times x squared would be x to the fourth. And then the rest of it would FOIL out correctly. And of course, x squared minus 9 is the difference of perfect squares. The x squared plus 4 is not factorable because it's a sum of perfect squares, so we'll just have to leave it be. What method do you want to try here? Grouping, right? We would look for a GCF to start with, but there isn't a GCF for all four terms. So we'll group the first two together. We'll make that subtraction a plus sign and put the negative with the 72, and then group the second two together. So what's the GCF in the first two terms? X cubed. And what would you be left with? And then what would be the GCF here? Negative 8. And what would you be left with? Okay, so it looks positive here for grouping because what was left over from each grouping is the same. So we'll take that out as 9x to the fourth minus y squared. And then what's left over will be an x cubed minus 8. we go any further with that? Yep. Difference of squares and difference of cubes. So factoring each of those, we'll get conjugates. It'll be 3x squared minus y and 3x squared plus y. And then difference of perfect cubes, we'll get a binomial and a trinomial. So x minus 2, x squared plus 2x plus 1. Everybody feeling good? Try that one. Where's that last one? Thank you. Recognize that that was a trinomial. There were 3 terms, and the middle term's exponent was half the first, so that indicates this is most likely going to be factorable, or at least we can attempt to factor this. And it turns out that it does factor into x cubed minus 8 and x cubed minus 1, each of which are the difference of perfect cubes. So we take the cubic root of x cubed and 8 to get x minus 2, and then SOPs will give us x squared plus 2x plus 4. And then x cubed minus 1, the binomial is x minus 1, and x squared plus x plus 1. Everybody good? All right, so on Tuesday, I know it's a 3-day weekend, but I'm going to trust that you're actually going to retain a little bit of this over the break, over the 3-day weekend. On Tuesday, we're going to come back to a quiz on all the things that we've done so far. So that would be sets and interval notation. That would be exponents. That would be linear models, and that would be factor. Okay, just a little lesson quiz. The grade will go in the classwork category. It's not going to go as a big assessment. It's kind of a little, just to see where we are and make sure that we're all in a good place before our test, which is right now, it's kind of scheduled for the end of next week on Friday. All right, so plan on a quiz when we come back on Tuesday on interval notation, sets, factoring, exponent rules, and on linear models. Okay. Your homework that I gave you back that you did in class on Wednesday, we have a few minutes, so I'll answer any questions that you have from that, because a lot of that material will be what's going to be on your quiz on Tuesday. So take that back out that I handed to you earlier. So you had this worksheet, which let's hold off on going over that because none of those problems are going to be on your quiz. They'll be on your next test, so we'll go over it again at some point. But how about any questions from any of these worksheets? Number 70 on which page? This is on that worksheet that you did in class on Wednesday. It's page 22 at the top, number 70. It's an exponent rules problem. You had a squared b to the negative 3 over x to the negative 1 y squared, all raised to the third power. And then x to the negative 2 b to the negative 1 over a to the 3 halves y to the 1/3. And all of that was just raised to the first power, so there really wasn't anything to do with that second parentheses. All right, so with these, we notice there's no addition or subtraction, so I'm going to distribute in any outside exponents, which we have an exponent of 3 on the outside, so when I distribute that in, that's going to be a to the 6th, b to the negative 9th, over x to the negative 3, y to the 6th. And then in the second parentheses, there was no outside exponent to distribute in, so we'll just leave it alone for right now. And of course, then we have the next step is to deal with any negative exponents. And so with all the negative exponents, they're just going to switch places. So in this first fraction, a to the 6th will stay, b to the 9th will move down, x cubed will come up, and y to the 6th will stay. So in the second fraction, it looks like everything is going to be in the denominator. Alright, so distribute in the outside exponents, move any negative exponents, and then we're ready to start simplifying. There's no numbers to deal with, it's just variables. So you have a to the 6th in the numerator, a to the 3 halves in the denominator. We'll subtract those. 6 minus 3 halves will be 9 halves. And where will that land? A to the 9 halves. Top. And then we have x cubed in the numerator and x squared in the denominator, so you just have an x in the numerator. And then a b to the 9th and a b both in the denominator, so that's b to the 10th in the denominator. And then both of your y's are in the denominator, y to the 6th and y to the 1/3, so we'll add those together and get y to the 19/3. Any other questions on any of this?
Number 67.
All right, this one comes from page 122, number 67, this worksheet. Sorry, I cut it off, I didn't realize. I hope you got all the information you need. Biologists have observed that the chirping rate of crickets of a certain species is related to temperature, and the relationship appears to be very nearly linear. The cricket produces 120 chirps per minute at 70 degrees Fahrenheit and 168 chirps per minute at 80 degrees Fahrenheit. And so it's already told you that the relationship between the variables is linear, so we can use a linear model. What are the two variables that we're dealing with in this problem? All right, temperature, and we'll call it the chirping rate. And of course, you always have to define one is the independent and one is the dependent. In this case, which would be which? What would be the independent variable? Temperature. Okay, so we'll treat that as x, and the chirping rate is y. Crickets do not determine the temperature outside. Right, their chirping rate is impacted by whatever the temperature might be. So if the chirping rate is 120 chirps per minute at 70 degrees Fahrenheit, that first point would be 70, 120. And the next one would be 80 and 168. So now we're ready to find our linear model by finding a slope. And what is that? 40 48 over 10, so 4.8. And then the equation would be, it does give us variables, specific variables to use. So I'll go ahead and just say y minus 120 equals 4.8 times x minus 70. But it tells us, I think it cuts it off, but it wanted temperature to be T. So which variable are you going to replace with T? X. And then it tells us that the chirping rate, the number of chirps per minute is N, so that'll be in place of Y. So when we solve this for N, we'll distribute in the 4.8 and then add the 120 over, and what do you get? 4.8 T minus, use my calculator. We'll get 4.8 times 70 and then add 120. Anybody? Second? 456. All right. Okay, so there's our linear model. And then it says that the crickets are chirping at 150 chirps per minute. Estimate the temperature. So we'll plug 150 in for N, and we can solve for T. I know you can figure that out if you need to. What does that slope represent in this particular problem? Fahrenheit. Good. All right. So for every 1 degree Fahrenheit increase, the number of chirps per minute increases by 4.8. The y-intercept in this problem really doesn't have a whole lot of significance, mostly because if we're at a temperature of 0 degrees Fahrenheit, there's really not going to be much of a chirping rate because they're all dead. Any other questions on this homework? Everybody good? All right, well, we will leave it there. Don't forget your quiz when you come Tuesday. And it's on factoring, linear modeling, exponent rules, and then sets and interval notation. Surely enough.